To us mere humans, the planet Earth feels incredibly vast. It takes days of continuous travel just to cross from one side of a single continent to the other, and weeks to sail across our massive oceans. But the moment you leave the fragile surface of our world and venture into the dark, it quickly becomes terrifyingly clear that we live on a microscopic speck of dust in a colossal, uncaring universe. It is a universe filled with innumerable rocky planets, swirling gas giants, and countless burning stars residing within trillions of slowly spinning galaxies. The universe operates on a physical scale that we simply cannot ever truly comprehend, let alone exhaustively explore in 1,000 lifetimes. But within this grand, terrifying cosmic structure lie individual beasts that, entirely on their own, defy our human understanding of scale. There are stars out there in the absolute dark so unimaginably large that they make our own life-giving sun pale into complete insignificance, and in the deep, cold depths of the southern constellation Scutum, astronomers believe that we have found the absolute largest one yet. But exactly how big can a star possibly get before the laws of physics tear it apart? And are there even bigger, more terrifying beasts waiting quietly in the dark to be found? Hello, and welcome to This is Space. I am Christopher, your guide through the infinite dark. If you deeply enjoy these atmospheric explorations into the unknown cosmos, please consider subscribing to the channel and leaving a thoughtful comment below. Your support allows us to keep venturing further into the deep mysteries of the universe, climbing the cosmic beanstalk into the kingdom of the giants of the universe. You might look up at the sky and naturally think our sun is a pretty big object, and from a human perspective, it certainly is. With a massive radius of nearly 700,000 kilometers across, it dominates our local space. To put that into a perspective, you can visualize, if the sun was shrunk down to the exact size of a standard football, the entire Earth would be 109 times smaller than that. Our entire world, with all its oceans, mountains, and billions of people, would be the size of a tiny 2mm wide peppercorn sitting next to it. Even if you mathematically added up all the total mass of every single planet in the solar system, including Jupiter and Saturn, the Sun would still be over 740 times more massive than all of them completely combined. The Sun contains over 99% of all the mass in our entire solar system. But when it comes to the rest of the stars scattered across the Milky Way galaxy, our Sun is absolutely nothing special. It is completely average. Some of our closest stellar neighbours, the Alpha Centauri binary stars, are a very similar size, and Sirius A, the brightest star in our night sky, is roughly twice as big and 25 times as luminous. But how big can a burning star actually grow before the fundamental forces of nature stop it? To truly understand that terrifying limit, we need to take a deep look at the violent process of stellar evolution. Our long journey begins here, in the mathematical heart of something known to astrophysicists as the Hertzsprung-Russell diagram. This incredible tool was independently invented in the early 1910s by both the brilliant Danish astronomer Einar Hertzsprung and the American astronomer Henry Norris Russell. It fundamentally plots the surface temperatures of stars against exactly how bright or luminous they truly are. And running diagonally straight down the center of this massive diagram lies a prominent band called the main sequence. This glowing spine of data is exactly where most stars in the entire universe spend the vast majority of their active lives. If a star is located here on the diagram, it strictly means that it is in a long, stable phase of existence. Having successfully survived the chaotic, violent collapse of a cold molecular cloud during its explosive birth, a main sequence star is now continuously, steadily fusing basic hydrogen atoms into heavier helium atoms deep within its pressurized core. This violent nuclear fusion generates unimaginable amounts of outward thermal energy that pushes aggressively outward against the brutal, crushing inward force of the own gravity of the star. It is an eternal, delicate balancing act of unimaginable physical forces, and once this perfect balance is finally reached, a star is scientifically said to be in a state of hydrostatic equilibrium. Almost all of the stars located on the main sequence are currently in this state of so-called physical rest, but that absolutely does not mean they are all exactly the same. Our Sun sits very comfortably right in the middle of the Hertzsprung-Russell diagram. It is a fairly average, stable G-type main sequence star. The letter G is what is called the spectral class of the star, a system which essentially classifies stars by their exact surface temperature, and therefore their visible colour. This fits into a seemingly arbitrary historical naming system of letters consisting of O, B, A, F, G, K, and M. In this specific classification system, the O-type stars are the absolute hottest, burning with a blinding blue-white intensity, and the M-type stars are the absolute coldest, glowing with a dim, sullen red light. Astronomers often remember this complex order using the simple mnemonic phrase, "Oh, be a fine girl, kiss me." You can do with that phrase exactly what you will. The Sun and other G-type stars have surface temperatures hovering around 5,778 Kelvin, which gives them the warm, comforting yellow-white hue that we're all so intimately familiar with on Earth. Deep inside, their dense cores steadily fuse hydrogen into helium, violently converting about 600 million tons of raw hydrogen every single second. This process emits the steady energy that, in the specific case of our Sun, has safely powered the evolution of complex biological life on Earth for billions of years. But if you move your gaze up or down the main sequence line, the physical nature of the stars radically changes, and a clear mathematical pattern begins to beautifully emerge. It is probably not entirely surprising to learn that dim stars are usually physically cool, and that the hotter a star gets, the significantly brighter it gets too, at least while it remains on the main sequence. But what might be significantly less intuitive to the human mind is exactly how the physical mass of a star directly relates to this brightness and heat, and there is a very clear, undeniable physical correlation. The absolute brightest stars also strongly tend to be the absolute most massive ones in existence. Take, for a prime example, Betelgeuse, which is the 26th brightest star in our night sky and forms the left shoulder of the famous Orion constellation. It is a massive B-type star, one of the absolute brightest classifications possible, and it has a scorching surface temperature of around 22,000 Kelvin. That makes it almost exactly 4 times physically hotter than the boiling surface of our Sun. It is also roughly 8.6 times more massive than our star. The violent physical effect of this much greater mass is to aggressively crush the hydrogen fuel in the core of Betelgeuse far more intensely than in smaller average stars. This infinitely greater pressure vastly increases the rate of the nuclear fusion reactions, and therefore far more blinding energy is violently released into space. This nuclear fusion is so incredibly powerful that it forces the entire star to physically swell outward. It is almost as if the massive gravity of the star cannot even contain the explosive energy it is generating. So, the total physical volume of Betelgeuse is a whopping 200 times greater than the volume of our Sun. But this immense size and blinding brightness comes at a terrible, tragic cosmic price. Massive main sequence stars burn incredibly hot and incredibly fast, while our quiet, average Sun will likely have a total peaceful lifespan of roughly 10 billion years. Betelgeuse has only been burning for about 25 million years, and astronomers estimate it only has a mere 7 million years left before it exhausts its fuel completely. This rapid consumption actually makes these very large stars quite rare in the galaxy. Their extreme instability and their incredibly rapid, fleeting existences mean we're simply far less likely to see them when we look up than their longer-lived, less massive red and yellow cousins. As we prepare to leave the relative safety of the main sequence and enter the realm of the true monsters, please take a moment to subscribe to This Is Space and leave a comment below. What is your absolute favourite star in the night sky? Let us know. So, is that the final answer then? If we truly want to find the absolute largest star in the universe, should we simply seek out the heaviest, most massive object possible? Astounding theoretical physics suggests that stars generally cannot grow much bigger than 150 times the mass of the Sun without becoming so violently unstable that the sheer outward pressure of their own radiation literally blows them apart, shredding the star before it can even fully form. However, the chaotic universe has found highly destructive ways to cheat when it comes to this fundamental physical limitation. When 2 already massive binary stars orbit too closely, collide, and violently merge together in the dark, the resulting Frankenstein star is a true, terrifying behemoth, much larger and more massive than absolutely anything possible, through the slow, standard devouring of a gas accretion disk. Perhaps this violent merger scenario is the exact explanation for the truly staggering and excitingly named star known as R136A1. Located deep within the Tarantula Nebula, a chaotic region of intense star formation in the Large Magellanic Cloud, R136A1 is potentially the absolute most massive and the absolute most luminous star known to exist anywhere in the observable universe. Sitting at the furthest top left point on our Hertzsprung-Russell diagram, R136A1 is an absolute, undeniable monster of nature. You can completely forget the theoretical 150 solar mass limit. This terrifying beast has been carefully mathematically estimated to be an unbelievable 265 times the mass of our Sun, and it currently has a radius roughly 40 times larger. It is part of a particularly rare, incredibly violent group of stars known to astronomers as Wolf-Rayet stars. We have successfully found just around 220 of these rare objects in our entire galaxy, although scientists statistically expect there could be as many as 2,000 hiding behind thick clouds of galactic dust. They are unimaginably massive, and they are currently in a highly advanced, incredibly short and terminal phase of their life, a phase that comes just moments before they completely collapse inward and detonate into massive, universe-altering supernova explosions. Because Wolf-Rayet stars like a 136A1 are so violently unstable, they continuously throw off vast, unimaginable amounts of superheated plasma in great destructive stellar winds. They are actively ejecting as much as 10 entire solar masses of material every single million years, blasting this heavy plasma out into the surrounding void at terrifying speeds of up to 3,000 kilometers per second. It is a star that is quite literally boiling itself to death, but they are also incredibly, blindingly luminous. The monster R136A1 is actively releasing as much total light in just 4 short seconds as our entire Sun produces in a full continuous year. Let that sink in. 4 seconds of its light equals an entire year of sunlight, although, ironically to our fragile human eyes, it actually only appears about 164,000 times brighter than our star. This is simply because the vast majority of its intense radiation is being emitted as invisible, highly energetic ultraviolet light, a frequency of radiation so powerful it would instantly strip the atmosphere from any nearby planet and sterilize the surface. To be completely honest, we are incredibly lucky to have caught a glimpse of this specific star at all. It will likely only exist in this current state for a maximum of 3 million years, which is barely the blink of a cosmic eye. It is burning the candle at both ends and in the middle. But incredibly, despite its staggering, record-breaking mass, this still is not the absolute largest star in the universe, not by physical radius at least. Because although it is certainly one of the most heavy and massive, there are far less massive stars that physically grow to be much, much larger in sheer volume. How is this possible? It turns out that the very largest stars in the entire cosmos have a brilliant physical trick hiding up their sleeves, or rather, hiding deep within their expanding outer shells. So far on this journey we have focused entirely on main sequence stars, those stable objects peacefully burning hydrogen fuel into helium within their dense cores. However, as a star eventually begins to die, that precious supply of core hydrogen will inevitably run out. And without the explosive, outward energy of core fusion to keep it perfectly stable, the intense, crushing gravity of the star finally begins to win the ancient battle, causing its deep inner core to suddenly start collapsing inward on itself. With this violent collapse comes an even greater, unimaginable physical pressure, which once again dramatically turns up the heat in the deep core. Eventually, the collapsing core becomes so incredibly hot and dense that it manages to kickstart a new process, helium fusion. This sudden ignition causes the star to boldly enter an entirely new chaotic phase of its life. But this intense new wave of heat generated by burning helium is also enough to violently warm the massive outer shells of the dying star. These outer layers can suddenly reach temperatures that used to only physically exist at the very center of the star, and suddenly, the dormant hydrogen atoms floating in the outer layers are also able to start violently fusing together. This shell-burning process causes the entire star to physically expand completely out of control, dramatically swelling in size as it officially becomes what is known as a red giant. Our own Sun currently has a modest radius of about 700,000 kilometers, But when this exact death process finally begins in about 5 billion years, the Sun will violently expand to a monstrous diameter of roughly 300 million kilometers. This massive expansion will make it completely big enough to utterly consume the planets Mercury, Venus, and most likely it will swallow the Earth itself, entirely vaporizing our oceans and melting our mountains back into magma. This tragic swelling process can take place in stars ranging from 0.8 to 8 times the mass of the Sun. A current, fascinating example of a swelling red giant is the mysterious star known as Mira A, which is a prominent part of the constellation Cetus. It is only between 1 and 1.2 times as massive as our own star, meaning it has roughly the same amount of actual matter, and yet its physical radius is at least 332 times bigger than the Sun. It is a swollen, bloated ghost of a star, and this massive size is just the baseline measurement. Mira A is highly unstable and actually physically pulses over the course of various cycles ranging from 80 to 1,000 days. When the internal mechanics of those specific cycles align perfectly, Mira physically puffs up even further, so its absolute maximum radius is actually much, much larger than the average. It can reach an incredible size of around 420 times the radius of our Sun. It is a breathing, dying giant. As we prepare to encounter the true titans of the cosmos, please subscribe to This is Space and leave a comment below. Does the thought of the Sun swallowing the Earth fill you with cosmic dread, or do you find it a beautiful natural cycle? But even a massive swollen red giant is not the absolute biggest type of star the universe can produce. When you look at stars that begin their lives with more than 8 solar masses, an entirely new, far more terrifying classification appears on the diagram. One that is even bigger, even more violent, and significantly more destructive. The red supergiant. Towering, mighty, and vastly larger than their smaller red giant cousins. These massive objects are also absolutely doomed to a sudden, incredibly tragic end. These glowing monsters of the universe will end their short, violent lives in an explosive, universe-altering supernova, leaving behind either a crushing neutron star or a bottomless black hole. But we are currently deeply interested in the quiet moments just before that final destruction, the thousands of years when they swell outward to become the absolute largest individual objects we can see in the universe. Betelgeuse is one of these doomed monsters. Forming the prominent glowing red shoulder of the constellation Orion, Betelgeuse is a familiar sight to stargazers on Earth. But its true physical scale is deeply terrifying. With a staggering diameter of roughly 1.2 billion kilometers, it is more than 700 times the physical size of our Sun. If you were to magically transport Betelgeuse and place it directly at the center of our own solar system, replacing the Sun, its glowing red surface would extend outwards so far that all the rocky inner planets, Mercury, Venus, Earth, and Mars, would be instantly, completely engulfed and vaporized. Even the massive gas giant Jupiter, located hundreds of millions of miles away, would likely not escape the burning outer atmosphere of this monster. Now these massive red supergiants are highly volatile, violent beasts. In the absolute last throes of their dying life, they pulse erratically and throw out huge, obscuring clouds of thick, stellar dust and heavy material. This constant, violent shedding actually makes it incredibly difficult for our astronomers to determine exactly where the physical edge of the star ends and the empty vacuum of space truly begins. It is like trying to measure the exact size of a thick fog bank. But despite its absolutely enormous, terrifying size, we mathematically know that even the mighty Betelgeuse is absolutely not the largest star out there. There is one other major, undeniable candidate for the throne, and as I heavily hinted at the very beginning of this cosmic journey, it lurks deep in the dark, dusty constellation of Scutum. This object is known as UY Scuti, and it is truly, fundamentally colossal. It is so unimaginably vast that an estimated 5 billion of our suns could physically fit completely inside its total volume. Let that massive number settle in your mind. 5 billion suns. Surprisingly, despite its incredible record-breaking size, it is actually not very physically hot. In fact, its surface temperature is roughly 40% cooler than the surface of our sun, and it glows with a dim, somber, incredibly deep red light. It is another classic dying red supergiant. Because of its vast distance from Earth and its relatively low surface temperature, UY Scuti is absolutely not visible to the naked human eye when you look up at the night sky. The light is too faint and too red. You need a pair of very powerful binoculars or a dedicated small telescope to even spot it hiding in the galactic dust. Located at a massive distance of somewhere between 5,000 and 10,000 light-years away near the centre of the Milky Way, there is still some significant scientific uncertainty about the true exact physical size of UY Scuti, with many other massive candidates occasionally vying for the ultimate title of the largest known star in the galaxy. But regardless of whether it holds the absolute number one spot, UY Scuti will absolutely not be around for much longer. It is already estimated to be between 10 to 20 million years old, which is ancient for a star of its massive weight class, and it may now only have a few scant million years left on the cosmic clock before its core completely gives out. Within that short remaining time, it may actually even get physically smaller in radius, transforming violently into what is known as a yellow hypergiant. This specific rare class of star is incredibly blindingly bright, radiating energy at a terrifying rate. But in order to achieve this state of extreme luminosity, the star would first have to violently physically shed almost all of its thick outer layers, blowing them off into deep space, thereby becoming physically smaller but significantly hotter in order to temporarily sustain the absolute last possible stages of nuclear fusion reactions in its dying core. These rare, unstable hypergiants are physically capable of completely blowing off a mass equivalent to the entire planet Jupiter in just one single explosive cosmic burp, and they have lots of these violent eruptions, filled with incredibly heavy, complex chemical elements like oxygen, carbon, silicon, and nitrogen that were forged deep within the nuclear furnace of the star. These massive ejected materials can quickly form vast, swirling clouds of dust extending 10,000 astronomical units in length. To understand that scale, that is roughly 300 times the entire distance from the Sun to the distant planet Neptune. It is a cloud of dust larger than our entire solar system, and these violent, messy deaths are absolutely vital to the continued development and evolution of the universe. These swirling, heavy expulsions of complex elements eventually mix with other cold dust clouds and raw material gathered from other dying stars, slowly combining over millions of years to create massive, dark stellar nurseries. These nebulae are literally filled with the exact chemical ingredients absolutely necessary for the creation of new rocky planets, liquid water, and ultimately, biological life itself. The iron in your blood and the calcium in your bones were forged in the dying heart of a giant star exactly like this. This final, beautiful destruction is still likely several 100,000, if not a few million years away for UY Scuti. But there is another giant star out there in the dark that is significantly, dangerously closer to this final, catastrophic destruction. For many years, we had only ever properly, directly imaged one single star located entirely outside the borders of the Milky Way galaxy, and it was a beast known as WOHG64. It was a massive red supergiant, a bit physically similar to UY Scuti, located a staggering 160,000 light-years away in the neighbouring dwarf galaxy known as the Large Magellanic Cloud. Recent, highly detailed astronomical studies strongly suggest that WOHG64 may have actually already physically turned into a yellow hypergiant. In just the last 10 short years of human observation, it has become significantly dimmer to our telescopes as it has violently thrown off massive amounts of heavy material and become completely, thickly shrouded in a dense cocoon of its own dying dust. The fundamental problem is, once you start looking at objects at these staggering intergalactic distances, it is incredibly difficult to measure things precisely. The dust obscures the starlight, making it look larger or smaller than it truly is. Maybe WOHG64 is actually physically bigger than UY Scuti. Maybe it is the true king. We simply do not have the visual resolution to know for absolute certain. But a bigger question remains: can stars theoretically get any bigger than this? We do not firmly know if stars can physically grow much larger than these red and yellow monsters. It is highly unlikely, as massive dying giants like UY Scuti are already violently scraping the very absolute edge of what astrophysicists call the Hayashi limit. This fundamental mathematical concept represents the absolute maximum physical size a star can ever possibly reach given its specific starting mass, and you can clearly see this physical barrier represented as a strict vertical line on the right side of the Hertzsprung-Russell diagram. If a bloated dying star physically crosses this theoretical line, expanding too far, then the internal forces of thermal convection inside the outer envelope take over, dropping the temperature, and the inward pull of gravity suddenly starts to strongly win the battle again, forcing the star to shrink back down and making it smaller. So, one day in the future, with better telescopes, we might find a star slightly physically bigger than UY Scuti hiding in the dust, but it absolutely will not be by much, unless we are completely, fundamentally missing something huge in our understanding of thermodynamics and gravity. Perhaps there is an entirely new, exotic type of giant star we simply do not currently have existing anywhere in our own galaxy. A type of star that only forms in the incredibly dense centres of elliptical galaxies, or one formed purely of dark matter. We simply do not know, and unfortunately, we do not currently have the advanced telescope technology required to peer deeply enough into other distant galaxies to definitively find out yet. What I do know, for an absolute certainty, is that the fragile human mind cannot really, truly wrap its head around absolutely anything physically bigger than a few thousand kilometres. Our brains simply did not evolve to calculate such vastness. So the sheer, terrifying physical scale of the biggest stars in the cosmos is completely, fundamentally far beyond our biological comprehension. They are true, undeniable cosmic monsters, burning with a ferocity that defies description. But in the grand, ultimate scheme of things, even these impossibly massive, bloated stars are incredibly, pathetically tiny. Entire galaxies are tens of thousands, or hundreds of thousands of light-years across, containing billions of these stars. These galaxies are situated millions of light-years apart from each other, drifting in the void, and individual glowing filaments of the massive cosmic web stretch for billions of light-years through the dark, cold space, holding everything together with the invisible hands of dark matter. The universe is so incredibly, terrifyingly vast that we cannot even begin to pretend to truly understand it all. But that absolutely does not mean we cannot bravely try to map it, measure it, and wonder at it. And as we have seen with the tragic, violent lives of the supergiants, physically bigger is absolutely not always better. The massive stars die young, in violent universe-shaking explosions, while the small, quiet stars live on for trillions of years. I think living peacefully on a tiny, stable, rocky planet, orbiting a completely average middle-aged yellow star is working out pretty well for us so far. It gives us the long, quiet time we need to look up at the dark sky and dream. Thank you for joining me on this incredible journey to the absolute limits of scale. Sleep well, keep looking up at the sky, and never ever stop completely wondering about the vast, terrifying, and endlessly beautiful universe we call our permanent only home.